Consider the wake left by a boat. Long after the boat itself has passed, the water is disturbed, carrying the memory of the disturbance, even as it settles. Now, scale that up to everything. We tend to think of events as finished. A star explodes, a particle decays, and the moment is gone. But what if it isn't? What if the universe itself is a vast, evolving record? What if every single event, no matter how small, leaves a permanent trace encoded in the very fabric of space-time? This isn't fantasy. It's a question pushing the edge of physics. If this kind of deep dive is what you look for, a quiet like or subscribe helps others find this space. Let's look closer at what it means for a universe to remember. Wherever you are right now, you are being held in place. The surface beneath you, the bed, the chair, the floor is supporting you. If we could remove the structure above you and the atmosphere itself, we would see the sky filled with stars, hundreds, thousands of them. Each one of these points of light is a tiny, glowing record. It is a message, not from this present moment, but from the distant past. This is where we begin. You have likely heard that looking at a star is seeing into the past. Light takes time to travel across the vast distances of space. A star that is, for example, 100 light years away, sent the light we see today 100 years ago. This means we are not observing how that star is, but how it was. In this simple fact lies an incredible concept. The sky is not just a view, it is a historical record. Every star, every faint shimmer of a distant galaxy is an old photograph. The light that makes up this starlight does not simply flicker and then disappear. It travels. It leaves its source and moves in a straight line, unless something massive, like another star or a black hole, bends its path. It keeps going. Some of this light will journey for billions of years, passing planets, dust clouds, and entire galaxies, undisturbed, carrying its message with it. It is a silent imprint of the moment it was created. Our eyes are part of this journey. When that ancient light finally reaches you, when it touches the surface of your eye or the sensor in a telescope, its long flight ends. For that one instant, that piece of history is seen. It is easy to forget this in our daily lives. We are surrounded by fast cycles of information. But outside of all that, the universe continues to send its memories toward us, not in words, but in light. This alone is a strange reality, but it becomes stranger the more we consider it. If light carries memories across space, then space itself is full of these old signals. It is not a stretch of emptiness. It is a slow, patient archive. This memory is not limited to light. Consider gravity. It feels like a constant, dull force. It is the pull that keeps you in your seat and makes objects fall. But gravity is also a form of memory. When a planet pulls on a moon, or a star tugs at a comet, it is because of where mass is located. Gravity is a consequence of mass. It presses into space and time, curving it. The path a planet takes around its star is not random. It is predictable because it follows the shape, the curve, created by the star's immense mass. The dance of planets and moons is a choreography based on this memory of where mass is. Space is not just something things move through. It is something that remembers where things have been. And this memory shapes the future. This effect is not limited to massive objects. Every tiny action leaves a trace. If you pick up a rock and move it, you have changed the local gravitational field. The change is microscopic, almost impossible to measure, but it is real. You have altered the layout of mass, and space has responded. When you flip a light switch, a current flows, and you change the electromagnetic field in the room. Even if you flip the switch off again, the trace of that event remains. Every interaction leaves something behind. This is where physical memory differs from human memory. Our brains are designed to forget. We lose information to make space, to let go. The universe, it seems, does not forget in the same way. It may not remember like a person does, but it holds everything. Every photon, every collision, every turn of a molecule is recorded as a change, as a shift in a field, as a scar in space. This raises the question, where does the universe keep all this memory? It is in the light, yes. It is in gravity, yes. But perhaps it is stored at an even deeper level, in the fundamental fabric of space-time, in the quantum fields that ripple beneath our reality. There is a theory, still debated but fascinating, that the universe is like a hologram. This does not mean it is a light projection. It refers to how it might store information. A standard hologram is a two-dimensional surface that can store all the data for a three-dimensional image. Some physicists propose that the universe might work this way. All the information inside a three-dimensional region, every particle, every interaction, could actually be encoded on the two-dimensional surface that surrounds it. This idea sounds impossible, but it is supported by the mathematics used to study black holes. One of the great puzzles of black holes is what happens to the information that falls in. If you throw a book into a black hole, does the story it contains disappear forever? That would seem to break a fundamental rule of physics. That information cannot be destroyed. The holographic theory suggests the information is preserved. It gets smeared across the edge of the black hole, the event horizon, and is stored there like a cosmic hard drive. It is imperceptible, but complete. If black holes can work this way, perhaps the entire universe does too. Perhaps your presence right now is adding to the data written into the cosmos. Even without this complex theory, we can see physical memory all around us. The fossil record is memory. Rocks that once flowed as lava now hold the trace of an ancient leaf. Ice cores drilled deep into glaciers contain tiny bubbles of air from thousands of years ago, a physical record of the atmosphere. Trees grow rings, recording wet and dry seasons. Canyons remember the water that carved them. The Earth itself is a library. If the stars are old messages, and if gravity is the memory of mass, it is a real physical question to ask. Does the sky remember you? When you stand under the night sky, you are not just seeing the stars. You are participating in a shared history. That starlight is completing a journey that began long before you were born. It traveled through the void just to reach the exact point where you are standing. Your presence mattered to the path of that light. But there is another layer. The moment you stand there, you are doing more than receiving light. You are also emitting it, not like a star, but as infrared radiation, as body heat. You are glowing softly, and that glow travels. You are not just looking at the universe, you are shining into it. Even now, you are sending out a signature, a real physical pattern of warmth that moves outward from your body. It spreads and diffuses, but it does not vanish. With the right instruments, someone could measure the change you made to the room you are in. Our technology makes this signature much stronger. Every time you make a phone call or use Wi-Fi, some trace of that signal spreads into space. The Earth itself has an electromagnetic fingerprint that is moving outward at the speed of light. Some of the earliest radio broadcasts ever sent are still traveling, now far beyond our solar system. They are faint and scattered, but they exist. The sky receives these signals. Most of this energy fades and mixes into the background noise of the cosmos, but that does not mean it never happened. The fact that it happened means that for one moment, the universe changed shape around you. Your body, your motion, your signal left an imprint on the field. This is the strange thing about physical memory. It does not require intention. You do not have to mean something for it to be remembered. You just have to be. The consequences of your existence ripple outward. When you lie under the sky and look up, there is a physical feedback loop happening. You are receiving the memory of stars, and the universe is receiving the signature of your presence. In physics, memory is not limited to minds. Memory can be encoded in the state of a system, in the position of particles, in field lines. Even the vacuum of space is full of structures, fields that stretch across the emptiness. These fields are sensitive. They respond, and when something passes through them, they shift. When that shift in a field occurs, the memory is written. There is a specific term for one version of this: the gravitational memory effect. This concept describes a permanent change that happens to space-time when a powerful gravitational wave, perhaps from two black holes colliding, passes through a region. Even long after the wave itself has dissipated, after the intense stretching and squeezing of space is over, the particles in that region do not return to their exact original positions. They remain slightly, but permanently, displaced. It is as if space itself remembers the event. This is not a speculative idea. It is a predicted consequence of Einstein's general relativity. So, the universe does remember. It may not catalog or interpret these events in the way a mind does, but it holds on to the physical changes. It holds the warmth from your body, the radio signals you send, and the tiny atoms you displace with every breath. Even in perfect stillness, you leave a trail. There is another, perhaps stranger, form of memory that emerges from quantum physics. This is the idea that particles do not just follow one single definite path from one point to another. Instead, they exist in a state of potential, exploring every possible path simultaneously. What we observe as reality is just one outcome, one path that becomes concrete. Importantly, some interpretations of quantum mechanics suggest that these unchosen paths, these might-have-beens, do not simply vanish. They linger as a form of shadow memory. They continue to interfere with and contribute to the reality we do see. When you move your hand or shift your weight, that action could have gone differently. The quantum wave function that describes you, in a sense, includes all of those possibilities right up until the moment of an observation, when reality settles on one choice. But the full equation, the history of all those potentials, continues to evolve. It carries the memory of what was possible alongside what actually happened. This is a difficult way to think of ourselves, not as solid, definite objects, but as a cloud of probabilities. But it is part of the physics. The underlying quantum fields may hold the complete pattern of what you could have been, in addition to what you are. All of this might seem remote, something abstract for physicists to consider, but if you lie still and think about it, it can change your sense of place. It changes the way you understand silence. It changes the way you look at the sky. Because the truth is, even if no one else sees you, even if you pass the day in complete quiet, the The universe knows you are here. It knows not with a mind, but with a physical record. There are molecules in the air that have brushed against your skin and are now forever altered. There are photons, particles of light, that have bounced off your hand and are now traveling outward into space, carrying that tiny piece of information. The sky and everything in it has felt your presence, and it will not forget. It may not assign meaning to you, but it will keep the record of the change you made. The question is not just whether the sky remembers you, but whether anything is ever truly forgotten. The light you send back, small and silent as it is, adds to the total pattern. Light does not forget where it came from. It just keeps moving forward. You do not have to ask it what it has seen. You just have to watch it arrive, because when it does, it carries the past. Every beam of light you have ever seen, every sunset, every reflection, every point of starlight started somewhere else. Long ago, light is a traveler. It crosses vast distances because it is patient, and it never stops until something intercepts it. If you look at a star a few hundred light years away, the light reaching you tonight left that star before your grandparents were born. That beam of light has been traveling for your entire life, and for many lives before yours. It does this simply because that is what light does. It keeps going. When it reaches your eye, it does not carry a message in words. It carries a fingerprint of the moment it was made. You are seeing its memory. This is true for everything you see. The light bouncing off a person's face takes a tiny fraction of a second to reach your eyes. When you see someone smile, you are technically seeing it just after it already happened. We only call it now because of the limits of our perception. For objects farther away, the delay grows. Light from the moon is about 1.5 seconds late. Sunlight takes just over 8 minutes to arrive. A signal from the edge of our solar system takes hours. From the next nearest star, it takes over 4 years. The farther the source, the deeper into the past we are looking. Light is not just illumination, it is record keeping. Unlike us, light does not get tired or fade in the middle of its journey. It keeps its message intact. This is how we know what the early universe looked like. The cosmic microwave background is the oldest light we can detect. It has been traveling for over 13 billion years. When a radio telescope detects this light, it is touching the afterglow of creation itself. This light is a precise record. Its tiny variations in temperature tell us how matter began to clump together, how the first galaxies started to form. Light does not embellish, it delivers what happened. Most of the light around you does not even reach your conscious awareness. It bounces, scatters, and reflects. But it is all there, connecting past and present. When you turn off a light bulb, the photons it already released are still going, traveling outward. From a photon's own perspective, time does not pass. The moment it is created and the moment it is absorbed are the same instant. But for us, that journey is long, and every photon becomes a memory. A photograph is just a record of light frozen in place. It is a way of catching time, but most light does not get caught. It escapes. This means there is more history moving through space right now than in all the libraries on Earth. There are beams from stars that exploded before life began, and some of in-transit light passes right through you. You are not just a receiver of light. You are part of its journey. In that way, you become part of the story it tells. You are not separate from the archive. You are inside it. Every second, the light touching your body is recording where you are. When that light reflects off you, it carries a trace of you, not your name, but your shape, your position, You are constantly shaping the light around you. You are part of the signal. That is not superstition. It is physics. Light is relentless and thorough. The next time you look at the stars, remember that you are not just seeing them, you are also being seen in the only way the universe sees, through energy, through interaction. Light creates a thread between what was and what is, between a distant star and your eye. If light is memory that travels, then gravity might be something even deeper. It may be a memory that holds on, not through travel, but through shape. You have probably thought of gravity as something ordinary. You do not need to understand it to know it is there. You drop something, and it falls. You stay grounded. But for something so constant, it is strange how rarely we question what it really is. We think of it as a pull, a downward tug. What if that is only half the story? What if gravity is not just a force, but a record? The way gravity works is not just about weight, it is about shape. According to the theory of general relativity, gravity is not a force in the way we usually think of it. It is not an invisible rope pulling objects toward each other. Instead, gravity is a consequence of the shape of space itself. A massive object, like the Earth, presses down on the very fabric of space-time. This creates a curve, much like a heavy ball placed on a stretched, flexible sheet. What we feel as gravity is simply us following the most straightforward path along this curve. We are not being pulled down. We are following the slope of the space we occupy. This is where the idea of memory enters. When a massive object moves through space, the shape of that space is altered. This change is subtle, but it is permanent. Space is not like an elastic sheet that springs perfectly back to its original flat shape. It is more like soft clay that holds the imprint of whatever pressed into it. The more massive the object, the deeper the curve it leaves behind. These curves, these distortions, can stretch across vast distances. The moon orbits the Earth, not because of some invisible tether, but because the Earth has so profoundly reshaped the space around it. The moon is moving along the contour of that curve, continuously following the path dictated by Earth's mass. In this very physical sense, gravity functions as a form of memory. The presence of mass alters the structure of space, and that altered structure then dictates how everything else in its vicinity must move. A planet remembers the star it orbits, not with a mind, but through the laws of physics. The planet's predictable motion is the physical result of that memory. This applies to everything, to comets, to other moons, to satellites, and even to tiny particles of dust. They do not have choices in their paths. They move the way they do because of the specific shape of the space they are in. And that space, in turn, is shaped by what has been there before. Even when an object moves on, its gravitational influence remains, spreading outward. This concept is not just a poetic phrase, it is literal. In physics, there is an established theory called the gravitational memory effect. When a very powerful event occurs, such as the merging of two massive black holes, it sends out ripples in space-time. We call these gravitational waves. As these waves pass through a region of space, they do not just push particles and then let them go, allowing them to return to normal. They alter the positions of those particles slightly, but forever. Space does not return to exactly the way it was before the wave. It remembers. That ripple, even when it becomes incredibly faint, carries the precise shape of the event that caused it. The source, the two colliding black holes, is long gone, but the effect of that event moves outward. A permanent mark is left in the structure of space, This has been supported by our equations for decades and has now been confirmed by observation. It is real. This might seem abstract, but it also applies to us. Here on Earth, your own body, your own mass, while incredibly small in the cosmic sense, still presses into space. It still curves it. The shape you create might be tiny, fading almost instantly into the much, much larger curve created by the Earth, but it is there. You bend space simply by existing. You are not just a passive object responding to gravity. You are an active participant in it. Every time you move, the curve you create moves with you. The world, at a microscopic level, reshapes itself around your weight and your presence. If a beam of light passed very close to you, it would bend, just slightly, because of the memory your body writes into the structure of things. This also works in reverse. The Earth curves the space you are in. The Sun curves it on a vastly larger scale, and the entire galaxy curves it on an incomprehensible scale. When you feel weight, what you are truly feeling is the slope of the space beneath you. You are trying to move in a straight line, but the curvature of space is constantly redirecting you downward. It does this not by pulling, but simply by redefining what a straight line actually is. That slope you feel is the product of a long history. It is the result of mass accumulating, of ancient stars forming and then exploding, of matter collapsing over billions of years to eventually form this planet. Your weight is not just the result of the Earth as it is now. It is the result of the entire history of matter that led to the Earth being here. Every atom in this planet is part of that chain, and every one of them has shaped the geometry you are resting in right now. This is why gravity does not let go. Space keeps its shape. It adapts, but it does not forget. Even if a star explodes, its gravity does not simply vanish. The memory of where that mass was, the shape it made, continues to spread. The gravitational influence stretches outward, rippling at the speed of light, never completely undoing itself. It only updates the record. So, when we ask if the universe remembers us, gravity answers, yes. It answers not with intention, but with shape. If you dropped a pebble into a perfectly still pool of water, the ripples would expand and eventually fade, but the pool would never be exactly the same again. The water would hold the memory of that disturbance. It is the same with space. The ripples of your presence are small, but they exist. This is seen on the largest scales. The stars in the sky are not just points of light. They are massive objects bending space across light years. Their gravity shapes how other stars move and how entire galaxies rotate. When a star dies, its gravity continues to shape the motion of everything around it. This is how black holes form as the natural, continuing influence of a star's gravity. Black holes take this memory to an extreme. Their curvature is so intense that it creates a boundary, an event horizon, but the memory remains. The gravitational pull of the black hole affects everything around it, shaping its environment. It may seem strange to call gravity a form of memory, but it is a system that preserves the structure of the past and uses that structure to determine the path of the future. It has been recording from the very beginning, from the first clumps of matter after the Big Bang. You exist in the middle of this long, continuous gravitational story. You are shaped by it, and you shape it in return. This is not a metaphor. It is just how mass and space behave. Because you have mass, you have influence. You leave a record. Therefore, when people say the universe is indifferent, that space does not care what we do, there is a truth to that. It does not assign meaning or judgment, but it does respond. It reshapes. It shifts. It holds on. We are surrounded not by an empty void, but by a structure, a fabric that bends with us and because of us. It is a quiet background that listens, not with ears, but with geometry. The space between the stars is often called empty. This word is a convenience, a simplification. If we paused and looked closely, not with our eyes but with the right instruments, we would see that even the quietest parts of the universe are not silent. Even where there seems to be nothing, something remains. What fills that space is not sound. There is no air to carry a whisper, but something does pass through, and it leaves a trace. That trace is an echo. It is not an echo that bounces off walls, but a more fundamental kind, a continuation of an event, stretched across immense distance and time. In interstellar space, far from any star, the density of matter is incredibly low, perhaps just a few atoms per cubic centimeter. To us, that is functionally zero, but those atoms matter. They move, they carry an electric charge, and they are influenced by magnetic fields. Their motion holds a memory of past collisions, of light that has passed by, and of ancient, distant supernovas. Much of that space is also filled with radiation, microwaves, radio waves, and X-rays, all drifting outward from past events. A star that exploded 10,000 years ago in a galaxy we will never see is still sending out its light and its particles. They do not vanish just because no one is looking. They keep going. The energy released in that moment continues outward unless it is interrupted. This means that empty space is actually full of old signals. They are weak, needing extremely sensitive equipment to detect, but they are real, and they are everywhere, passing through this room and through your body, right now. Our observatories are powerful because they listen to this in-between space. Radio telescopes are not just looking at stars, they are tuning in to the ancient radiation between them. The quietest parts of the sky are not blank. They are filled with overlapping histories, signals so faint they just seem like background noise. This is how we discovered the cosmic microwave background. It was found not by pointing at a specific galaxy, but by measuring the static noise coming from every direction. It was a faint, uniform hum, an echo from when the universe was only a few 100,000 years old. That signal had not disappeared. It had been traveling the whole time. When we finally built instruments quiet enough to hear it, it was still there. It is not just light that travels. Particles do, too. Cosmic rays and high-energy fragments of atoms journey through space for millions of years. And there are neutrinos. These particles are created in the hearts of stars and in distant galaxies. Countless numbers of them pass through your body every single second, without interacting, without you ever feeling them. But they carry energy, and that energy comes from events long gone. The universe spreads these events out, like ink in water. The moment does not end. It continues, thinned out, but always moving. This is what makes empty space so interesting. Not what it lacks, but what it quietly contains. Even gravity reaches into that space. When two black holes merge, the gravitational waves ripple out in every direction, moving through the void. As they pass, they stretch and squeeze space itself, leaving that gravitational echo, the memory effect. We cannot feel it, but our instruments, like LIGO, can measure it. They detected a change in distance smaller than the width of a proton. It was enough. It was proof that something had happened far away, and its ripple had reached us. Space is not just where things happen. It is how we know they happened. Just as we receive these signals, we also send them. Earth is not silent. Our planet radiates heat and reflects sunlight. And for over 100 years, human technology has flooded space with our own signals. A television broadcast from 1953 is now over 70 light-years away. A radar ping from decades ago is halfway to a nearby star system. These signals degrade, but they do not disappear. They are a footprint. When we think of space as silent, it is only because we are used to sound needing air. But in space, silence does not mean nothing is happening. The vacuum does not resist or erase. It lets things move without interference. This lack of friction preserves events in motion. A signal in space can last, potentially crossing the entire observable universe. Space is permissive. It carries. It holds on. The universe, at this very moment, is full of events that have not finished echoing yet. Events that happened long ago are still in the process of arriving somewhere, still shaping the background noise of the cosmos. This includes you, your signals, your body heat, and your personal electrical field all extend out into space. They may not travel far, and they may not be strong, but they are enough to join the countless other echoes. They are enough to leave a trail. What is fascinating is that none of these echoes are coordinated. There is no editor, no central archive organizing this data, but the fundamental structure of space itself holds them all together. The quantum fields, the curvature of space-time, and the states of particles all respond to one another. They all adapt and change slightly with every new interaction. This implies that memory, in a physical sense, does not require a mind. It just requires a medium that can be changed, a medium like space itself. Now that we understand that even a vacuum is not truly empty, it is worth asking, if all these echoes are still out there, can we ever truly lose anything? Does forgetting mean the same thing if the universe is constantly carrying the evidence forward? Is silence really the absence of memory, or is it just a layer of information we have not yet learned to read? These questions do not need immediate answers, but they can stay with you quietly. They are like the particles that drift unseen through your room, or the background radiation that warms you ever so slightly. They are like the gravitational field that curves gently around your weight, holding you in place. The next time you look at the dark sky, try not to think of it as blank. Think of it as layered, full, and alive with quiet evidence. If space can carry echoes, and if even the emptiest regions hold onto the past as ripples and waves, there is one place in the universe that seems to defy this pattern. There is one place where forgetting does not just happen, but appears to be the absolute rule: a black hole. You have probably heard the basics. A black hole forms when an extremely massive object collapses under its own gravity. It squeezes its matter into a point so impossibly dense that nothing, not even light, can escape its pull. It does not explode. It folds inward. What is left behind is not a solid object or a hollow void. It is a region of space where gravity has become absolute, where the slope of space-time becomes so steep that everything light, matter, energy falls in and cannot come out. This makes them sound like cosmic vacuum cleaners, but they are not. They do not suck things in from across the galaxy. They just sit there, quietly, waiting for something to cross their boundary. That boundary has a name: the event horizon. Once something crosses the event horizon, escape is no longer possible. This is not because it is being crushed, but because the paths leading out no longer exist. From that point on, all possible directions point inward, toward the center. This much is well understood. It is backed by observation, theory, and mathematics. But black holes have always raised a deeper, stranger question that does not fit easily into our understanding of physics. The question is not about what they are, but about what they do to information. Imagine throwing something into a black hole. It could be a book, a single particle, or a beam of light. Once it crosses the event horizon, it is gone from our universe. You cannot pull it back. You cannot scan it or retrieve its data. From the outside, the only things you can ever measure about the black hole are its total mass, its spin, or angular momentum, and its electric charge. That is it. You cannot know the details of what went in, not its composition, its structure, or its identity. This is a profound problem. In all other known areas of physics, information is never supposed to be truly lost. This is a core principle. You can scramble information, like burning a book. You can hide it or make it practically impossible to reconstruct. But in theory, the information is still there, in the smoke, the ash, and the heat. If you knew every detail about a system, you could, in principle, reverse the process and recover what it was. This idea is called unitarity, and it is a foundation of quantum mechanics. Black holes seem to violate this. They appear to erase the fine details of everything that falls into them. If you dropped a page of writing and an identical mass clump of iron into the same black hole, the end result would be indistinguishable from the outside. The information, the words, the atomic structure of the iron would be gone, forgotten by the universe. This violates everything else we know. Physicists call this the information paradox. The debate is not about whether black holes exist. We have observed their effects clearly. The debate is about whether they break this fundamental rule of reality. In the 1970s, Stephen Hawking made this problem even more precise. He showed that black holes are not entirely black. They radiate. This is not light escaping from the inside, which is impossible. Instead, it is a quantum process happening right at the edge of the event horizon. Pairs of virtual particles pop into existence, and sometimes one particle falls in while the other escapes. That escaping particle carries energy away from the black hole. This means the black hole slowly evaporates. It loses mass over vast, unimaginable periods of time. Eventually, it could disappear entirely. If that is true, then all the information that ever fell into the black hole seems to vanish along with it. The book, the particle, the light, their patterns and identities are not just hidden, they are erased. This is the paradox. If black holes can destroy information, then quantum mechanics, our most successful theory of reality, must be wrong. But if quantum mechanics is correct, then black holes must be keeping the information somehow, somewhere. But where? For a long time, no one knew. Some suggested the information is stored deep inside the black hole, encoded in the central singularity. Others propose that the information actually does come back out, hidden in the faint Hawking radiation, but it is so scrambled that it just looks like random noise. Another idea led to something much bigger, the holographic principle. This idea suggests that the information is preserved on the event horizon itself, on the thin, two-dimensional surface at the edge. The black hole acts as a kind of memory surface, a ledger. This theory proposes that everything inside a volume of space can be described by information stored on its outer boundary. The universe, in this view, might work like a hologram, where a flat, two-dimensional surface encodes a full, three-dimensional volume. Black holes inspired this idea because the only traits we can measure, mass, spin, charge, are traits of the surface. Perhaps the details are stored there too. There is also a concept called black hole complementarity. It suggests that the information is not lost. It just depends on your point of view. If you stay outside the event horizon, you see the information fall in and become encoded on the surface. But from the perspective of an object actually falling in, the information still exists and passes through the horizon with it. Both descriptions are seen as valid, but they cannot be accessed at the same time. We do not know which of these ideas, if any, is correct. But it is clear that black holes are not simple endings. They are not oblivion. They may be the most compressed, hidden record keepers in the entire universe. It is tempting to think of a black hole as forgetting, as a page torn from the book and burned. But even fire leaves ashes and follows rules. Gravity, despite its power, also obeys structure. It does not just destroy, it transforms. Perhaps what we call forgetting is just a form of compression, an encoding so complete that we cannot yet decode it. This matters because the universe is full of transformations. Stars collapse, matter combines, and energy radiates. Nothing stays in its original form, but every single transformation follows rules. If information could truly be lost, then cause and effect itself would become uncertain. The structure of physics would unravel. That has not happened. Even black holes leave clues. If black holes can store the memory of everything that falls into them on their surface, then something strange opens up. Maybe that is not just a black hole thing. Maybe that is how all of space works. This is the root of the holographic principle. It is a serious proposal. When physicists calculated the maximum amount of information a black hole could hold, they found something shocking. The limit was not based on the black hole's three-dimensional volume. It was based on its two-dimensional surface area. This breaks our everyday logic. We expect the contents of a room to scale with the size of the room. But for black holes, the surface holds the key. So, what if this is true for the universe itself? What if the entire three-dimensional volume of space, every particle and event, could be fully described by information encoded on a distant, two-dimensional boundary, like a cosmic screen? This sounds abstract, but it has strong mathematical support. In certain models of space-time, you can take a complex system of gravity in 3 dimensions and describe it perfectly with a simpler system of particles and fields on a flat, 2-dimensional boundary. The physics match. It is like 2 different languages telling the exact same story. One language is space with gravity. The other is a flat surface with no gravity, only particle interactions. If this holds, it means everything happening inside the universe might be a projection of information that lives on its edge. Not a movie, not an illusion, but a mathematical equivalence. What happens in the bulk of space is fully accounted for by what is stored on the surface. In this holographic view, the event horizon of a black hole is not just a point of no return. It is a ledger. The information that goes in is encoded there, flattened onto the surface. Now, if that works for black holes, what is the boundary of our universe? Our universe does not have a physical edge. It expands without a center. But in the mathematics that describe space-time, it is still possible to define a boundary at infinity, a region that, in theory, contains all the information about what is inside. The holographic principle does not need a literal wall. It just needs a surface that encodes the contents. From that surface, one could, in theory, reconstruct everything happening inside. Not just the positions of galaxies, but the quantum states of every particle. Your hand moving, a thought forming, all of it, theoretically, written on the edge. This is not proven for our universe, but the idea is taken very seriously. It connects gravity and quantum mechanics in a way few other ideas can. It treats information as the fundamental ingredient of reality. The holographic view says the universe is not made of matter first. It is made of information first. Matter and energy are just the expressions of that information. This reshapes how we think about memory. If information is fundamental, then memory is not just something brains do. It is something space does. It is something reality cannot avoid doing. As you move through a room, you leave a trace in the fields around you. When you shift the configuration of matter, that motion is encoded. You sit still, you breathe, and the state of space updates. That update is not deleted. It becomes part of the whole. The question of whether the universe remembers does not rely on a mystical awareness. It relies on the idea that everything is information, and that information is conserved. Even when your mind drifts and your thoughts fade, the underlying physical pattern of your presence continues to exist. It is a contribution to the total state of the universe. You are not isolated from the rest of space. You are entangled with it. This is not a metaphor. In quantum mechanics, entanglement is a real, measurable phenomenon. Two particles can share a single state so that measuring one instantly influences the properties of the other. No matter how far apart they are, their information is correlated. Some physicists now believe that space-time itself might be built from this entanglement, that the structure of the universe and the force of gravity emerge from vast networks of shared information. If that is true, then memory is not something layered on top of reality. It is reality. The separation between past and present is not absolute. It is relational. It depends on how the information is accessed. In this view, forgetting is never complete, not because you remember everything, but because the system does. The totality remembers. You only see a slice, a single moment, but the whole is still there. You do not need to visualize the edge of the universe. Just know that you are part of it. You are not outside the pattern. You are written into it. If you have ever wondered whether your smallest actions matter, physics says yes, not in a grand performative way, but in the structure, the state, and the encoded shifts in the fabric of what is. You have likely heard the word entropy. It is often used to mean disorder or chaos. But in physics, entropy has a more specific meaning. It is about information. Entropy is a measure of the number of ways a system can be arranged internally while still looking the same from the outside. It is a count of all the possible configurations. Think of a new deck of cards, perfectly ordered by suit and number. You know exactly where every card is. This is a low entropy state. Now, shuffle that deck. From the outside, it is still just a deck of cards. But on the inside, the number of possible arrangements has skyrocketed. Your knowledge of where any specific card is has dropped to near zero. This is a high entropy state. The same idea applies to physical systems. A container full of gas molecules has high entropy because the molecules are all moving in random directions. You cannot predict where any single one is. Entropy is a measure of the information you have lost, or never had, about the precise state of the system. Here is the most important part. entropy almost always increases. This is the second law of thermodynamics. In an isolated system, entropy does not go down. It only stays the same or goes up. Things spread out. Structures decay. Order becomes harder to maintain. Ice melts and smoke disperses, not because a force is pushing them apart, but because there are vastly more ways for things to be disordered than to be ordered. The universe naturally flows from low entropy to high entropy. This is one of the few physical laws that gives time a direction. Most equations in physics do not care if you run them forward or backward, but entropy breaks that symmetry. It creates the arrow of time. This is why you remember the past, but not the future. It is why a glass shatters but does not spontaneously reassemble. The ordered states are simply fewer and less likely. We experience the flow of time as this change in entropy, as a shift from order to disorder, as a dilution of information. This has direct consequences. Every time you remember something, your brain creates a specific pattern, a connection between neurons. This is a low entropy state. It is vulnerable, and it takes energy to maintain. Over time, those patterns degrade. This is why memories fade, not because they were poorly formed, but because they are physical structures, and structures are fragile in a universe that favors disorder. A computer storing data must also fight entropy. It uses energy to keep bits aligned and temperatures stable. The moment the power is lost, the memory starts to decay. The cost of keeping a memory is energy. The cost of forgetting is nothing. It happens on its own. This might sound bleak, but entropy is also what allows for change. Without it, everything would be static and frozen. There would be no flow, no difference between moments. Entropy gives time its texture and its meaning, but it does mean that most memory is temporary, because it exists in a system that naturally tends toward forgetting. And yet, some things resist, some structures hold. Stars burn for billions of years. Atoms remain stable. A fossil holds its shape. These things are not immune to decay, but they last. They preserve a record of what happened. This is the balance. Entropy pulls toward forgetting, while physical systems push against it to remember. The same is true of you. Your body maintains its form against entropy, at least for a while. Your thoughts, your habits, your posture, all are forms of physical memory stored in repeated structures, and each one takes work to preserve. This is why rest and sleep matter. Maintaining form in a world of entropy requires constant repair. When you think about forgetting, cosmically, it is not about destruction, it is about diffusion. The signal does not vanish, it just spreads out. The pattern does not die, it just becomes less distinct. Information does not disappear, it redistributes. The laws of physics never say memory is impossible. They only say it is expensive. It costs energy and structure. The cosmic microwave background radiation, for example, started as bright, high-energy light, dense with information. But as space expanded, that light stretched and cooled. Now, it is just faint background noise. The history is still there, but it has diluted a high-entropy record that is much harder to read. Memory does not disappear. It just becomes harder to find. Time is the one thing you are always moving through. You do not have to do anything to pass through it. You are not just in time, you are made from it. Every process in your cells, every memory in your brain depends on time passing. And it passes in only one direction, forward. This forward motion is not a habit, it is a law. You eat, then you digest. You remember after something happens. This sequence is never optional. It is because the universe itself is wired this way. Time flows one way because entropy flows one way. This means that time, in practice, is a record. It is the structure that keeps track of change. Without change, if all particles were frozen, time might still exist, but you would not be able to perceive it. There would be no then to compare with now. Memory and time are completely dependent on each other. You cannot have a memory without time, because memory is a record of what used to be, and you cannot perceive time without some kind of change, some new information that marks a difference. This is why the universe seems to remember. It is not writing things down. It is simply that the state of things now is a direct consequence of the state of things before. The shape of a galaxy reflects the motion of matter billions of years ago. The energy of a particle reflects what it just interacted with. It is all connected through cause and effect. Time is the network that links those causes and effects. Everything you do adds to this timeline. Even in stillness, time carries your signature forward. That is how memory works at every level. When a rock falls into a river, the splash is temporary, but the erosion, the new shape of the riverbank that is a memory, when light passes through a cloud of gas, the atoms in that gas absorb and then re-emit very specific wavelengths of light. That absorption pattern, its unique fingerprint, is a memory of the gas's composition. When two particles interact and recoil, their new trajectories carry the physical mark of that interaction. That is also a memory. None of this can happen outside of time. It happens because of time. It can be helpful to think of time not just as a line, but as a medium, something that surrounds you. It is not visible or solid, but it is always there. You are immersed in it. You feel this when you reflect on a moment and recognize that it is past, that it was once present and now it is not. That distance between the experience and the recollection is time. You do not create it, you inhabit it. And time is not the same everywhere. Time moves differently depending on your speed and how close you are to a massive object. This is a core part of general relativity. Gravity slows time down. An astronaut orbiting the Earth ages just slightly more slowly than someone on the surface. A clock on a mountaintop ticks just a fraction faster than one at sea level. These effects are small, but they are real and measurable. Global Positioning System, or GPS. Satellites must constantly account for these time differences. If they did not, your phone's location would drift by kilometers every single day. This tells us something crucial. Time is not absolute. There is no single, universal now that stretches across the entire cosmos. Now for you is different from now for someone moving at a different speed or in a different gravitational field. This means the universe's record isn't like a single, synchronized book. It's more like a vast collection of overlapping, interconnected diaries, all written at slightly different speeds, but all part of the same story. Time is local, but within your own frame of reference, it feels continuous. You build memories as you go, and you compare new experiences against those old memories. This is how you construct meaning. Time is the medium where meaning accumulates. Even fundamental particles use time. A particle traveling through space has a history, a trajectory, and properties that evolve. They are not static. In this way, everything in the universe has a timeline. Every star, every atom, every event. and these timelines intersect. When you touch something, your histories combine. You leave a trace and receive one in return. When you look at an object, the light reaching your eyes has been traveling for some time, bringing a piece of the past with it. You are always interacting with time, modifying it locally and briefly in the patterns you leave behind. This is what makes memory possible, not just in the mind, but in matter itself. Your brain remembers in a biological way, with neurons connecting and chemical pathways strengthening. But those changes are physical. They happen in time and are carried forward. The reason you can recall something from years ago is because that physical structure has lasted. The timeline did not break. The same applies to the universe. Its structure lasts, not in perfect detail, but enough to build stars, form elements, and sustain orbits. All of this depends on continuity. Time flows forward. The past does not vanish. It accumulates. That is what history is. It is the physical memory of the universe, encoded in rocks, in radiation, in the rotation of galaxies, and in you. You are not separate from this timeline. You are an extension of it. The patterns in your body reflect billions of years of chemical evolution and planetary motion. You are composed of moments that preceded you, and you will continue into the moments that follow. You do not need to remember everything. The universe does that, not as a consciousness, but as structure, as persistence, as time. By now, you have heard that your body is made of stardust. The carbon, the calcium, and the iron in your blood all came from older stars that lived and died long before the Earth formed. This is true, but what is often missed is what this means on a deeper level. It means your body is not just made of matter, it is made of memory. This is not memory as your brain keeps it. There are no photographs or names. It is memory as a sequence of conditions that had to be met, a long line of events that had to happen in just the right way for you to exist. Start with a single atom in your body, a nitrogen atom in your bloodstream. That atom was not made on Earth. It was forged inside a star much more massive than our sun. That star lived for millions of years, crushing lighter elements together in its core through nuclear fusion. It had to reach the precise temperatures and pressures necessary to create that nitrogen atom. Then, that star had to die in a particular way, likely a spectacular supernova explosion, to scatter those newly forged elements, including your nitrogen atom, out into the space between stars. Those contents had to mix into a vast cloud of gas and dust that, over millions of more years, condensed to form our solar system and the planet Earth. On Earth, complex chemistry happened, slowly and consistently, until that atom was taken up by a plant, eaten by an animal, or consumed by you, eventually becoming part of a cell in your body. That single atom is a literal, physical record of all those conditions. Its existence now is the direct result of that unbroken continuity. Your structure holds more than your life. It holds cosmic history. Your DNA is a different kind of story. It is a chemical sequence, a molecule that holds instructions, and those instructions have been passed down, generation by generation, for billions of years. The shape of your proteins, the design of your cells, the way your body heals all of it, is built on patterns that were copied, modified, and copied again. Some of those patterns go back to the earliest single-celled organisms. This process of filtering natural selection is itself a form of memory. The environment asks what works for survival. and the DNA that is passed on is the memory of the answer. You are not the first version, you are the current one. Scientists can look at your genome and find evidence of ancient viruses embedded in your chromosomes. They can trace your ancestry through changes in your DNA. All of that is memory, encoded chemically, not consciously. Then there is physical memory, the way your bones grow, the way your muscles hold your posture, the way your immune system reacts. These are learned responses, accumulated experiences. Your body carries scars, not just visible ones, but cellular ones, chemical adaptations based on prior exposure. This is also memory. It does not require awareness. It is just what happens when structure meets time. Even your senses are built on memory. Your ability to see is the result of light-sensitive proteins that evolved over eons. Your brain interprets signals from your eyes and ears by comparing them to patterns it has already learned. Memory is not something you switch on. It is embedded in the very act of perception. All of this rests on an even older story, the laws of physics. The fact that electrons still carry the same charge, that photons still travel at the same speed, and that gravity still curves space. This consistency is the most basic form of memory there is. Without it, nothing could last. So, when you feel the weight of your body, you are not just feeling gravity. You are feeling a summary, a compression of everything that had to happen for you to be here. Your body obeys rules written before you were born. That is what makes you more than just matter. You contain its history. You are not random. You are assembled. Everything has a past, and that past is traceable, embedded in your structure. Your body carries that memory quietly, even when you are asleep. This continuity also means that pain can be passed down, that trauma can leave marks, and that habits can become generational patterns. But it also means that growth is possible, that healing can be structural, and that new stories can be written. Because memory is not only about what was kept, it is also about what can be changed. At the smallest subatomic scale, memory gets strange. You are used to thinking of matter as stable and solid, but beneath that surface, matter behaves very differently. It is in constant motion and interaction. So, does matter, in its most basic form, remember where it has been? A particle like an electron does not have thoughts, but it does have properties: mass, spin, and charge. These properties persist. That persistence is already a kind of identity, a memory of what it is. Beyond identity, there is interaction. When two particles meet, they exchange momentum and energy according to specific rules. These exchanges leave marks. The particles that emerge from the interaction are different. Their new paths reflect the event. What a particle is doing now contains information about what it did before. We know this because of the conservation laws. The laws of conservation of energy, momentum, and angular momentum are like the grammar of the universe. They are strict rules for how memory is transferred. In quantum mechanics, a particle's state, all of its possibilities based on its history, is described by a wave function. This function is a complete record. When the particle interacts with something else, the wave function updates or collapses. This change isn't an erasure, it's the creation of a new memory, a new record of the event, which is then carried forward. A particle cannot just forget its past. Its current behavior is fundamentally dependent on it. Let's look at matter on a larger scale. The behavior of a cell is built upon the behavior of the molecules within it. Those molecules are built from atoms, and those atoms are governed by the interactions of tiny particles. This is a layered system. At every level, those interactions carry a record. An electron, for example, does not circle an atom's nucleus the way a planet orbits a sun. It exists in a cloud of probability. The shape of that cloud, its specific energy level, is determined by the atom's history, the forces it has felt, the bonds it has formed, the other particles it shares space with. That electron's state is a physical summary of its past. When two atoms collide, they are altered. They exchange energy, they vibrate differently, their paths are changed. That alteration, that change in energy or position, persists. Matter holds on to the shape it has been given, at least for a time. We can see this in the world around us. When a crystal forms, its final pattern is determined by its environment, the temperature, the pressure, and any impurities in the solution all guide its growth. If you look closely at a crystal, you can often see tiny faults or inclusions, a speck of another mineral, a tiny trapped bubble. These are not just defects, they are records. They are physical notes, a timeline of what happened during the crystal's formation, like a diary written in stone. Metals also possess this kind of material memory. If you stretch or bend a piece of metal, the particles inside it, arranged in a neat grid or lattice, are forced to shift. Some of these shifts are not reversible. They become a permanent dislocation in the structure, a history locked into its lattice. With the right tools, you can read the forces that shaped an object long after those forces are gone. When we go even smaller, into the quantum realm, particles have states, and those states evolve. If a system is perfectly isolated from the rest of the universe, its evolution is predictable. But most systems are not isolated. They are open. They interact constantly with their environment. This interaction with the outside world is called decoherence. Decoherence is what makes the strange, blurry quantum world start to look like the classical, solid world we are used to. It is also what makes quantum memory extremely fragile. The moment a quantum system interacts with the outside world, even with a single stray particle, a cosmic ray, or a tiny vibration from heat, it begins to lose its fine, detailed structure. This is why building quantum computers is so difficult. They are revolutionary because they use these quantum states to compute, but they rely on keeping a system perfectly isolated, long enough to preserve a specific quantum state, a memory. If too much decoherence happens, that memory collapses into simple noise. So, at the smallest, most precise level, particles seem to forget easily. And yet, at the larger scales we live in, the opposite seems true. The patterns formed by those particles can be incredibly stable. A rock remembers the shape it was given by erosion. Layers of sediment pressed together for millions of years remember the pressure that turned them to stone, holding the fossils of ancient sea creatures. A tree remembers the direction it grew toward the light. Your hand remembers the shape required to hold a pen. This stability exists not because every single atom is fixed in place, but because the overall structure is reinforced. The structure persists even as the individual particles fluctuate. Radiation also carries memory. When a particle decays, it emits energy. The type and direction of that energy tells us what the original particle was. We use this principle to study distant stars by analyzing the light they send. We also use it to date the Earth. The radioactive decay of elements like uranium, which turns into lead at a fixed rate, acts like a clock. By measuring the ratio of uranium to lead in an ancient rock, we can read its history. one atom at a time. So, matter does keep a record. It is not written in symbols, but in structure. Every interaction changes something, and that change persists as long as the system itself persists. Even temperature is a form of memory. A hot object has energy distributed among its particles. That energy had to come from somewhere. Friction, sunlight, a flame. The heat is not just a sensation, it is history. It tells you that energy was added to the system. Until that energy is lost, the memory remains. Your surroundings are full of this silent information. A worn spot on a floor remembers where people walk. A door that sticks in the summer remembers the moisture in the air. A faded curtain remembers the sunlight that has passed through it. We read these material memories constantly without thinking about it. When you get small enough, down past the molecules and atoms, you reach a place where the rules are entirely different. This is quantum mechanics. Things no longer have exact positions or definite speeds. They exist as probabilities, as chances, as shadows of what they might be. In this quantum world, certainty is limited. You can measure a particle's position, but in doing so, you lose precise knowledge of its momentum. You can measure its energy, but you give up precision in time. These are not errors in measurement. They are fundamental features of reality. Memory here is delicate, because to observe a quantum system, you must interact with it, and interaction changes it. A quantum system left alone evolves smoothly, like a wave unfolding. But the moment you look, that wave of possibilities collapses. You do not see a blur. You see a single, definite result. The rest of the possibilities vanish. This collapse is what makes quantum memory so fragile. You can only preserve a quantum state if you isolate it completely. The possibilities that vanish are sometimes called quantum shadows. They were real, but they were unchosen. A famous experiment illustrates this: the double-slit experiment. If you fire a single particle, like an electron, at a barrier with two slits, something strange happens. If you do not measure which slit the particle goes through, it acts like a wave. It seems to pass through both slits at once and interferes with itself on the other side. This creates a specific pattern on the screen behind the barrier. But the moment you place a detector to see which slit the particle used, the interference pattern disappears. The particle behaves like a simple projectile, going through one slit or the other. The act of observation, the act of measuring it, forces it to choose one path, and the shadow of the other path vanishes. In this quantum world, silence is not emptiness, it is potential. It is a system that has not yet been asked to choose. This concept is also what makes entanglement so strange. Two particles can become connected in such a way that they share a single state, a single shared history. If you measure one of them, you instantly affect the state of the other, no matter how far apart they are, even if they are on opposite sides of the galaxy. This is not a signal traveling between them. It is a shared memory. When they were created, their properties were linked. When you measure one, you collapse the wave function for both of them. This quantum correlation is surprisingly resilient against distance, but it is just as fragile to noise and interaction as any other quantum state. This is the constant balance. Memory is preserved in isolation, but to read the memory, you must interact with it, and that interaction often ends the quantum state. The particle doesn't look back, but its current structure, its now, contains the trace of before. The universe continues. Possibility, then collapse. Shadow, then signal. There is a point where the very small becomes large again. The quantum rules give way to the biological, and the biological begins to ask questions. You live at this scale, where molecules build cells, and cells build patterns that can think. You do not just observe the world passively, you interpret it, you reflect, and that introduces something new to the universe. Not just structure, not just interaction, but awareness. You are not the only part of the universe that responds to input. A leaf moves in the wind, a rock heats in the sun, but you do something different. You experience the input, you track it, you form a memory of it, and then you build something on top of that memory. Meaning, the patterns in your brain are physical. They are not magic. They are chemical signals and atoms obeying the same laws as everything else. But when enough of this structure exists, billions of neurons, trillions of connections, something recursive emerges. The ability to reflect on your own response. You do not just feel warmth. You remember how warmth feels. You do not just see light. You recall where you saw it before. That recursive loop, awareness feeding back on itself, is what gives rise to memory as you know it. This awareness, this processing of memory, creates something else. It creates a sense of identity. This is the feeling of being a continuous self, a single you that exists across time, connecting your past experiences to your present moment. This raises a wider question. If the universe, as a physical system, remembers, and you are a part of that universe, is your own mind just one small part of a much larger process? Is your individual awareness one thread in a much larger fabric? There is no direct answer, but there are patterns in the cosmos that are worth noticing. When astronomers map the universe on the largest scales, they do not see an even, random spread of galaxies. They see a specific structure. This structure is called the cosmic web. It is made of vast, long strands or filaments of dark matter and gas. Where these filaments cross, they form dense, massive clusters of galaxies called nodes. In between these filaments are enormous, mostly empty regions called voids. This entire web stretches for hundreds of millions of light years. This pattern is not random, and it looks surprisingly familiar. This large-scale structure of the universe bears a striking resemblance to a biological neural network, like the connections inside a brain. The similarity is not just in how it looks, it is also in how it functions. The dense, galaxy-filled nodes act like major hubs of activity, similar to important processing centers in a brain. The filaments act as pathways, channeling matter and gas from the voids toward the nodes, much like neurons transmit information along axons. This structure, this cosmic web, is a system that allows matter, and, by extension, information, to move and interact in a complex, organized way. On Earth, a very similar kind of structure, the brain allows for the process we call thought. This leads to a specific question. Not does the universe think? That implies a human-like consciousness. The question is whether the universe, as a physical system, could host processes that resemble thought. Some researchers are exploring this, not through mysticism, but through computer models and information theory. They ask if consciousness is something unique to biology, or if it is an emergent property. Emergence means that complex, new behaviors can arise from simple, interacting parts. If a system has enough complexity, enough connections, and a way to process feedback, awareness might arise even without neurons. If that is the case, the universe itself, at this massive scale, becomes a candidate. It is not a candidate for having opinions or feelings, but it is a candidate for being a system that contains memory, responds to physical changes, and evolves based on feedback. This is, in essence, what your brain does. It is an adaptive system. It takes in sensory inputs from the outside world. It stores those inputs as physical patterns, as memories. It then uses those stored patterns to make predictions about the future, and it guides your actions based on those predictions. When the result is different from the prediction, it corrects itself. This loop input, memory, prediction, correction, is the definition of an adaptive system. The universe, as a whole, is also an adaptive system, though it operates on an almost unimaginable timescale. Over billions of years, it does evolve. Simple structures, like the first stars, formed. Those stars created heavier elements, which allowed for new structures, like planets, galaxies, collide and merge, changing their form. Within these systems, new layers of complexity emerge, such as life, and eventually, minds. So, perhaps your mind is not separate from the universe's memory at all. Perhaps it is one of its instruments. Perhaps the human mind is the part of the universe that has, for the first time, become complex enough to notice the rest of itself. This would make your thoughts not a break from nature, but a fundamental extension of it. When you reflect, when you remember, when you imagine a future that has not happened, that could be seen as the universe, through you, folding its own memory back onto itself. You are compressing physical experience into abstract symbols and then using those symbols to construct new scenarios based on old patterns. This recursive, self-reflecting quality is rare. Rocks do not do it. Rivers do not do it. But minds do. And your mind is made of the same matter as the rocks and rivers. Your thoughts are carried by particles that used to be inside stars. The system that now contains your awareness is not separate from the cosmos. It is built from it. In this view, memory is not only stored in atoms, or in radiation, or in the curvature of gravity. It is also stored in perception. It is the record of a moment held not just by a particle, but by a mind. Your brain, of course, cannot remember everything. It is not a video camera. It must filter. It trims away details. It emphasizes certain information, and it discards most of what you experience. But even these choices about what to keep and what to discard are shaped by past patterns, by feedback, by what you have previously learned is important. The brain is not a perfect recorder. It is a meaning engine. Its job is to extract useful structure from the noise of reality. This gives us a layered idea of memory. At the base level, particles remember their state through the laws of conservation. Above that, atoms remember their history through their arrangement in molecules. Above that, matter remembers its past through its physical structure, like the shape of a canyon. And at our level, minds remember through experience. Each level builds on the last. Each one filters and processes information in a different way, but none of them are separate. This is the key. Your brain sits inside your body. Your body sits inside space. Space is shaped by mass and energy, and all of it follows the same fundamental rules. Those rules are what create the patterns that form everything, from distant galaxies to the neurons firing in your head. When you think, you are not pulling something from nowhere. You are using a network that was shaped by the cosmos, a biological machine built through billions of years of iteration. You are not the whole brain of the universe, but you might be one of its neurons. And if that is true, every act of memory is not just personal, it is participatory. It is the universe, in a small, brief way, becoming aware of its own structure in the form of your thought. This deep connection leads to another kind of memory. This one is not stored in particles, but is passed between people. It is stored in language, in culture, and in stories. There are moments in life that feel strangely familiar, as if they have already happened. You walk into a room for the first time, or you hear a voice, and a powerful sensation washes over you. I have seen this. I have been here. This already happened. This sensation is known as déjà vu. It is a common human experience, but it does not come with a clear explanation. It is not a literal replay of a past event. It is a moment when your present experience aligns with your brain's expectation of that experience so perfectly that it feels like a memory. Inside your brain, scientists believe déjà vu is likely caused by small glitches in timing. Your brain has different pathways for processing perception and for tagging that perception as familiar or new. A slight delay in one of these signals, a loop that forms for just a millisecond, could make a brand new, incoming perception feel like an old, recalled memory. But outside your brain, the universe itself has its own form of déjà vu. This is not a feeling, but a physical fact. It is the appearance of the same patterns over and over at completely different scales. Think of a spiral. You see it in the tiny, coiled shell of a snail. You see it in the massive, swirling arms of a hurricane. And you see it on the grandest scale, in the shape of a spiral galaxy hundreds of thousands of light years across. These spirals are not copies. The galaxy did not learn from the seashell. They form the same shape because the fundamental laws of physics that shape them are consistent. The universe does not need to invent new rules every time. It just lets the same conditions like gravity, rotation, and fluid dynamics play out. This is not an accident. It is a result of symmetry. Symmetry is one of the most powerful ideas in physics. It means that if you can change something about a system, for example, move it or rotate it and it still looks and behaves the same, that system has a symmetry. These deep symmetries in the laws of nature are what lead to the conservation laws. And conservation laws, in turn, create regularity. Regularity is what makes repetition possible. You see it in the orbit of a planet around its star, or the cycle of a moon. These are not identical every single time, but they are extremely close. This repetition creates structure, and structure is what allows memory to be held. So, déjà vu on a cosmic scale is not about a shared experience. It is about recurrence. It is about systems that echo themselves, not because they remember the past, but because they are forced to obey the same rules, and those rules produce similar outcomes. These recurring patterns show up everywhere. The distribution of galaxies in the cosmic web follows a specific mathematical pattern. If you zoom in, you find similar branching patterns in the neural networks of a brain, in the way a river branches into deltas, in the way lightning forks, and even in how a tree grows its branches. This is not a mystical connection. It is mathematical. Systems that are governed by feedback loops, by thresholds, and by rules of growth under constraint will naturally converge on these same efficient forms. They do not copy each other. They simply arrive at the same solution from different paths. This is what gives the universe its feeling of familiarity. It feels familiar not because it is small or predictable, but because it is coherent. You are not surrounded by pure, unstructured randomness. You are surrounded by structure. And that structure shows up again and again in forms that your brain is specifically evolved to recognize. When you feel a moment that seems to repeat, it might not be just an internal brain glitch. It might also be your brain recognizing a fundamental pattern of nature. Stable systems settle into cycles. A binary star system with two stars orbiting each other will repeat that orbit for billions of years. A pulsar, which is a collapsed, spinning star, flashes beams of light in beats that are more precise than an atomic clock. These are not memories in the human sense, but they are consistent, repeating behaviors. And in those behaviors, the universe leaves a predictable record marked in time. Even the light reaching you from a distant star arrives in waves. Those waves have a frequency, and frequency is, by its very definition, a repetition. So, you see the same cycles playing out at all levels, light waves flickering, electrons oscillating, molecules vibrating, and your own heart keeping time. Your own sense of identity depends on this. If your body forgot its fundamental rhythms, it would not survive. If your mind lost its consistent patterns, you would not know who you are. So much of what gives the universe its structure is this repetition. It is because everything emerges from the same set of interactions. Gravity curves space the same way here as it does in a distant galaxy. Electromagnetism obeys the same rules everywhere. The fundamental forces do not change. From these constants, familiar forms take shape. A spiral in your fingerprint, a spiral in a storm, a spiral in a galaxy. Something in your brain, the pattern-matching machine, says, I have seen this before. Maybe that is not a trick. Maybe that is your awareness picking up on the fact that the universe has memory, not just in matter, but in its very structure. It builds the same shapes again and again because those shapes work. They are stable, they persist, they balance forces and conserve energy. This is what memory looks like when it is not about events, but about stability, and you are built to notice that stability. Your brain evolved to spot patterns, to find rhythms, to detect faces in noise. This ability keeps you safe, but it also allows for wonder. You live inside these loops, and these loops shape your perception. So, cosmic déjà vu may not be a glitch. It may be recognition, not of a specific place, but of a structure, a form that has appeared before and will appear again. It is not that the universe repeats itself in a perfect circle, but that the conditions that made something once can and will make it again. When something feels familiar, perhaps you are picking up on a real echo not from your own past, but from the deep, structural memory of the world. You do not have to be alive to remember something. That idea might feel strange, because memory feels personal. You remember your first school, the taste of something sweet, the feeling of cold air on your face. It is tied to awareness, to identity. But memory in the physical sense is not limited to the living. It can exist anywhere. Structure persists through time. A rock cannot think. It does not feel. But if it is cracked on one side, that crack is a record of force. It holds information about pressure, temperature, and time, not in a conscious way, but in a physical one. The shape of that break, the specific minerals exposed along the edge, and the layering of the material all tell a story of how that rock came to be. No mind is needed for that record to exist. The same is true for a pattern of ice on a window. It is not a random design. The delicate, branching, crystalline shapes are a direct result of the specific conditions in the room. They depend on the exact humidity, the precise temperature of the glass, the flow of air, and even tiny, invisible specks of dust that act as starting points for the crystals. When that pattern freezes into place, it becomes a perfect, temporary snapshot of those variables. The ice did not intend to remember, but it did. This kind of memory, the kind without intention or awareness, is everywhere. It is what allows fossils to form. When an organism, like a leaf or a shell, falls into soft mud, it leaves an impression. Over millions of years, that mud is compressed by the weight of new layers above it, and its minerals slowly change, turning it into solid rock. But the shape of the leaf, the impression, can be preserved. This is a passive memory. Nothing tried to store the information. The structure simply survived. And persistence is all that memory truly needs. Heat leaves a mark. Cold leaves a mark. Even just the passage of time leaves a mark. Consider the rings of a tree. A tree does not know it is recording time, but its body is a precise diary of its life. Each year, it grows a new layer of wood just beneath its bark. In the spring and early summer, when water is plentiful, the tree grows quickly, and this new wood is typically lighter in color and less dense. In the late summer and fall, growth slows, and the wood becomes darker and denser. This contrast creates one visible tree ring. You can read this pattern like a diary. A wide ring tells of a good year with plenty of rain and sunlight. A very narrow ring tells of a drought. A dark, triangular scar embedded in the rings tells the story of a forest fire that happened decades ago. The tree did not mean to write any of this. It was simply responding to its environment, and that response was physically recorded in its own structure. The same logic applies to human-made objects. A building settles over time. Wood warps. Paint fades where the sun hits it most. A concrete sidewalk, after decades of use, will be visibly worn down along the exact path where people walk every day. The material itself, the concrete, keeps a physical record of repeated use. It does not have to understand footsteps to record their impact. In this way, the universe is full of memory, not because it is watching, but because it changes, and each change leaves something behind. This is true at the largest scales. The surface of a planet remembers what has hit it. The moon is covered in craters from ancient impacts. Those craters, some billions of years old, are still there, almost perfectly preserved. This is because the moon has no active memory erasing systems. It has no atmosphere, which means no wind or rain. It has no plate tectonics, no geological activity to recycle its crust. The moon's surface is a static, ancient archive of past collisions. Earth is different. Our planet is active. It has wind, water, and ice that constantly erode its surface. It has plate tectonics, a process where the crust is slowly pulled back into the planet and melted, destroying old records. To find Earth's oldest memories, you have to dig deeper, past the active surface, into layers of rock or deep into polar ice. Or you can look inside the atoms themselves. Atoms also keep a kind of memory. This is how we know the true age of the Earth. A sample of ancient rock, for example, will contain a certain amount of the element uranium. Uranium is an isotope, which means it is an unstable version of an element. It naturally and spontaneously changes or decays over time. A uranium atom will eventually turn into a stable atom of lead. This decay happens at a perfectly steady, known rate. This rate is called a half-life, which is the time it takes for exactly half of the uranium atoms in a sample to decay into lead. By measuring the ratio how much uranium is left compared to how much lead has been created, scientists can calculate exactly how long that rock has existed. No mind is involved. It is just physics. It is a clock built directly into matter. So, memory without a mind is not rare. It is the constant, underlying principle of how the universe works. Even the light around you contains it. A single particle of light, a photon, does not have a brain, but all of its properties are information. The path it takes, the energy it carries, and the direction it moves all tell a story about where it came from. When we measure that light, we are reading its history. In some cases, that history is ancient. Light from the most distant galaxies has been traveling for billions of years to reach our telescopes. As that light travels, the universe itself is expanding. This expansion of space physically stretches the light waves. This is similar to how the sound of a siren is stretched to a lower pitch as it moves away from you. When light is stretched, it becomes redder. We call this redshift. By measuring how much a galaxy's light has been redshifted, we can infer not just its distance, but its age. The past is literally reaching us in the present. If memory is just the survival of change, then the universe is full of it, and your own body stores this physical memory, too. Your bones are not static. They are constantly remodeling themselves, becoming denser in areas that bear more weight. Your joints reflect your history of motion. Your skin reflects sun, time, and repair. Even if you had no conscious awareness at all, your body would still carry the record of what has happened to it. A person in a coma is not forming new conscious memories, but their cells are still reacting, their tissues are still adapting, and their DNA is still replicating. This is the important distinction. Memory can exist without being experienced. Awareness uses memory, but memory does not require awareness. You live inside a layered world. You are conscious of a tiny fraction of it. You remember some of your childhood, but you do not remember the formation of your organs. You recall some conversations, but you do not remember the constant, perfect replication of your DNA. And even if you were to forget everything you have ever known, the world would still remember your presence in the worn shoes, in the chair that holds your shape, in the changed air. There is one form of memory that was never written down. It was never stored in a book, encoded in a brain, or carved into stone. It happened all at once, everywhere, and it is still unfolding. You live inside it. It is the afterglow, the oldest light in the universe. We call it the cosmic microwave background, or CMB. Roughly 13.8 billion years ago, the universe was not cold and dark. It was unimaginably hot, dense, and opaque. It was so hot that atoms could not hold together. It was just a soup of free-floating particles, protons, and electrons. In this environment, photons, or particles of light, could not travel. The instant a photon began to move, it would collide with a free electron and be scattered in a random direction. The entire universe was glowing, but that glow was trapped, like being inside a dense fog. Then, something changed. The universe was expanding, and as it expanded, it cooled. After about 380,000 years, the temperature dropped low enough for the slower-moving electrons to be captured by the protons, forming the first stable, neutral atoms. This event, known as recombination, changed everything. A neutral atom does not scatter light the way a free electron does. For the photons, the fog instantly cleared. The universe became transparent. The light that was released in that moment, from every single point in the cosmos, has been traveling in a straight line ever since. It is still moving. It is still all around us. It is still arriving at Earth from every direction. After traveling for over 13 billion years, the expansion of space has stretched that light. It is no longer a bright, hot glow. It has been redshifted all the way down into the microwave part of the spectrum. Its temperature is now just 2.7 Kelvin, only about 3 degrees above absolute zero, the coldest possible temperature. But it is not zero. It is a faint, persistent, real glow. This is the longest memory. It is not stored anywhere. It is just still, in transit. It has been patiently moving across the expanding void. Scientists have mapped this background light in incredible detail. It is not perfectly uniform. There are tiny, microscopic differences in its temperature. These tiny fluctuations are not noise. They are the most important information we have. They are the seeds of all structure. The slightly denser, cooler spots were the places where gravity had a tiny extra pull. Over hundreds of millions of years, these spots pulled in matter to become the first stars and the great clusters of galaxies. The CMB is a blueprint of the universe's childhood. This memory is not distant or theoretical. It is present. On an old analog television, when it was tuned to an empty channel, that snow or static hiss was not just random noise from the antenna. A small percentage of that static, about 1%, was the television picking up the cosmic microwave background. It was the afterglow of creation, the oldest memory in the universe, arriving in your living room in real time. That is how the universe remembers. It does not forget. It just moves. It stretches. It changes in form, but not in content. The CMB tells us that there was a moment of transition, a moment when light was released. And because that moment happened everywhere, the memory is everywhere. All of this unfolded while that background light kept moving, undisturbed. Silence does not feel like information. It feels like the absence of it. When sound stops, you are left with stillness. It is easy to treat that stillness as empty, but not all silence is the same. The silence after a loud thunderclap tells you something happened. The absence of sound is a marker. It provides context. The universe uses this too. The vacuum of space has no air, so there is no sound, but its silence is also interactional. Space is so vast and empty that particles can travel for billions of years without hitting anything. This lack of interference is what preserves signals. It is why the ancient light of the CMB can reach us. Space does not erase. It just does not interrupt. It is a silence that preserves memory by refusing to overwrite it. This happens in the deep ocean. Below the noisy surface, in the immense, still darkness, there is very little noise. In that quiet, whales can communicate over enormous distances. The silence of the deep does not erase their songs, it preserves them. In some systems, silence is the only way memory survives. When you speak, your words vanish. But when you stop speaking, the listener reflects. That reflection happens in the space you leave behind. The same is true in music. The notes matter, but so do the rests, the intentional moments of silence between the notes. A phrase becomes powerful not just because of what is played, but because of what is withheld. Silence is not an absence of information. It is often a necessary condition for processing it. Your brain, for example, needs quiet to consolidate memory. This is not a passive act. It is one of the primary functions of sleep. During the day, your brain is busy recording new experiences. A region called the hippocampus is highly active, taking in sensory details and short-term information. But this storage is temporary and not very stable. When you sleep, the brain begins a complex reorganization. During deep, non-rapid eye movement sleep, the brain starts to sort through the day's events. It replays important patterns, strengthening the connections between neurons that were used. This is consolidation. The brain physically moves important memories from the temporary storage of the hippocampus to the vast, long-term storage of the neocortex. At the same time, it also prunes connections, weakening or removing unimportant or redundant information. This essential sorting and filing does not happen during the noise of the day. It happens in the quiet. This is also true for emotional processing. When you experience something intense, your nervous system is in an active, high-alert state. You are focused on reaction, not reflection. The deep learning, the integration of that experience, comes later. It happens in the quiet, when the perceived threat is gone and your body returns to a state of calm. You remember and process events better when you feel safe, because that safety allows for the silence needed for access and integration. This principle extends beyond biology. In technology, silence protects memory. A qubit, the basic unit of a quantum computer, holds its information in a fragile, coherent state. This state is a blend of all possibilities, but if that qubit interacts with anything, a stray particle, a vibration, a tiny change in temperature, the silence is broken. The system decoheres, and the complex quantum memory instantly collapses into simple, classical noise. To work, a quantum computer must be almost perfectly isolated, shielded, and kept in a state of extreme quiet. The natural world uses this same mechanism. A glacier, for example, is a massive record keeper. Its movement is so slow, its internal change so gradual, that it functions as a system of immense stillness. As snow falls each year, it compacts into ice, trapping tiny bubbles of ancient air. Scientists can drill deep into this ice, pulling out ice cores that are thousands of feet long. By analyzing the air trapped in those bubbles, they can read a precise, year-by-year history of the Earth's atmosphere, temperature, and climate, going back hundreds of thousands of years. That physical record only survives because the glacier is a system of immense, cold stillness. The absence of activity is what preserves the memory. This is the same principle behind archival science. You reduce the variables light, heat, moisture to create a form of silence. In that silence, the record holds. In physics, a quiet state, a state of stable equilibrium, is often just a pause before a massive change. This is called a phase transition. Think of liquid water at exactly 0 degrees Celsius, 32 degrees Fahrenheit. It is in a stable, quiet state. But if you remove just a little more energy, it does not simply get more cold. It fundamentally transforms. It abruptly reorganizes its structure, transitioning into a new, more ordered state, solid ice. The universe does this on a vast scale. A vast, cold, quiet cloud of hydrogen gas can exist in a stable state for millions of years. It is perfectly balanced. But a small disturbance, a tiny gravitational ripple from a passing star, can break that silence. It can cause a small part of the cloud to become just slightly denser. This new density creates a stronger gravitational pull, which pulls in more gas, which makes it even denser. This feedback loop, which began in a quiet, stable system, results in a catastrophic collapse. The center of the cloud ignites. A new, complex, energy-producing structure, a star is born. This process is called emergence. It is the way complexity arises from simple, quiet beginnings. Life itself is an emergent property. It did not appear from chaos. It arose from a quiet, stable chemical environment on the early Earth, where conditions were calm enough for complex molecules to form, interact, and eventually build self-replicating structures. This raises the question of the ultimate fate of memory. If structures hold records, what happens when all structures end? The second law of thermodynamics states that, in an isolated system, entropy or disorder always increases. Left alone, things fall apart, energy spreads out, structure becomes noise. This law points to a possible future for the entire universe, a scenario sometimes called the Big Freeze or the heat death. In the far, far future, trillions of years from now, all the gas needed to form new stars will be used up. The last stars, the small, slow-burning red dwarfs, will finally dim and go out. The universe will become cold and dark. Over unimaginable stretches of time, matter itself may decay. The remaining black holes will slowly evaporate over eons, particle by particle, through Hawking radiation. Eventually, the universe may be left as nothing but a vast, cold, uniform, and expanding soup of disorganized particles. In this final state of maximum entropy, no complex structures can exist, no patterns, no records, and no memory in any form we recognize could survive. From this perspective, yes, the universe will ultimately forget, not by choice, but simply through the relentless passage of time. But this is not the only way to look at it. A fundamental principle of physics suggests that information, at the most basic quantum level, is never truly destroyed. This is the core of the information paradox concerning black holes. If a black hole evaporates, what happens to the perfect record of everything that fell in? The emerging theories suggest the universe must, at a fundamental level, keep that record. It is not erased, it is transformed. This implies that the present state of the universe is a direct and complete physical consequence of the state that came before it. The laws of physics are a form of perfect accounting. Your existence and your actions are not separate from this. You have altered the arrangement of atoms. You have sent out signals. The light that is bouncing off your body this very second, carrying the information of your presence, is now traveling outward at the speed of light. That signal will be stretched, and it will grow faint, but it has been added to the cosmos. That event cannot be undone. You exist in the middle of this vast, layered process. The atoms in your body hold the physical memory of the stars that forged them. Your DNA holds the chemical memory of billions of years of evolution. Your mind holds the neurological memory of your own experience. The patterns you hold and the patterns you change are not outside of nature. They are a part of its complex, evolving structure. When you wonder what the universe remembers, you are already part of the answer. You are not just an observer of this memory. You are an active participant in its creation. Every motion you make, however small, alters the gravitational and electromagnetic fields around you. Every breath you take changes the chemical composition of the air. That change, no matter how microscopic, becomes a new, permanent part of the total state of the cosmos. The difference propagates outward. It does not need to be recorded in a book to be real. It does not need to be remembered by another mind to have happened. The difference you make exists, and it does not require permanence to be complete. The light that left your skin a moment ago is still traveling. It may scatter, it may fade, but it went somewhere. In that movement, the universe adjusted. That is true of everything. Nothing you have touched is exactly the same as it was. No breath you have taken was neutral. The change remains. It is not remembered as a name or a face or a story. It is remembered as influence, as a permanent, physical difference folded into the ongoing state of the universe.